Okay, today is February 9th. So we are here right now. So we have a quiz and assignment one. So I will open quiz one tomorrow morning because the quiz will include some questions about the maximum likelihood estimation. Okay, so today we will learn about the maximum likelihood estimation, and I will open quiz one tomorrow morning, 9 a.m. You have 24 hours to take a quiz one, but there is no time limit, but you can take only once. Okay, so and then they are all most of them are the multiple choice, but a couple questions will be very short, short answer question. Okay. So and then assignment one will be out this Thursday, and you will have 1 week to complete assignment one. So assignment one will be about the reviews of statistics and matrix algebra and maximum likelihood estimation. Okay. So I will, yeah. Do you guys have any question about the quiz and assignment? No? You're excited about that? I'm sorry. Okay, so right. So the last class, we talked about the matrix algebra, right? So let me briefly review the matrix algebra, and then we'll finish the matrix algebra. So we talked about the vector, and we talked about the matrix and eigenvalue, eigenvector, determinant, and transpose, and diagonal matrix. You talked about some basic concepts of matrix algebra. So vector is one dimension of the matrix, right? So for example, let's say vector is 1, 2. This is vector, column vector. And then matrix can have a row and column. So in this case, I will say 1, 2, and what is that? 3 and 1. Okay. So role of matrix is to make a linear transformation, right? So if we multiply this vector and matrix, it will be 1 times 1 plus 1 times 3, right? And then 2 times 2 plus 2 times 1. So it will be 1 plus 4 and 6, right? So after multiplying matrix, this vector become this vector, right? So which means originally this was 1, 2, 1 and 1, 2. So this vector becomes 1, 2, 3, 4 and 1, 2, 3, 4, 5, 6. This vector, right? Do you follow me? So, but some vectors can make some vectors can be identical after transposing. No, I'm sorry. After linear transformation by matrix, which means, for example, in this case, this is matrix A. This is vector X. After multiplying, after linear transforming based on this matrix algebra, and it will be lambda times X. So we still have same vector, but it is lambda times. So this vector, after linear transforming, and then this vector can be this vector. But this vector, two vectors that can be overlapped. So this vector is called eigenvector, right? And then this lambda is called what? Eigenvalues, right? So eigenvalue and eigenvectors are really important to understand the data reduction. When we talk about exploratory factor analysis and principal component analysis, we will use these concepts. Okay. So this is some basic concepts of that. Okay, so next question is how to find it, how to find the eigenvalue and eigenvector. So this is the definition, right? So after transforming this vector by this matrix algebra is equal to some constant times this vector. So this is AX is equal to lambda times identical matrix. So identical matrix is like just one, okay? So it's still lambda. So, and then times X. So it's right here. And then this is AX minus lambda IX is 0, right? So, and then we can pull out A minus lambda I times X equals 0. Do you follow me? Okay, so now we have this formula, and then X is vector, right? So by definition, X should not be 0 because X is vector in this case. So in order to make a 0, so this should be 0, right? So, okay, so how can we find the eigenvalue in this case? So, oops, I'm sorry. So two vectors on the same line. So what would be the determinant of these two vectors? What is determinant? 0, right? Because these two lines overlapped. So determinant is the area or volume of a vector or matrix, but they overlap. There is no area, right? So that's why we got this determinant. Determinant is 0, okay? So you already learned about this one, A, B, C, D. Let's say this is A matrix. What is determinant of A? So that is A times D minus B times C, right? So we learned about it. So let's compute this one. It's right here. Let's say this is A matrix. Okay. And then we will find the determinant. So A minus lambda I. So this should be lambda times 1001, right? So this is lambda 0, lambda, right? So A minus this one should be like this because 2 minus lambda, we subtract element by element. And 1 minus 0 is 1, and 1 minus 0 is 1, 2 minus lambda is 2 minus 1. And then we can find the determinant. So this one times this one is right here, minus 1 times 1 is right here. This should be 0. And then if you solve these equations, you will get this one. And then lambda square minus 4 lambda plus 3 is 0. So it should be like this. Lambda minus 1 times lambda minus 3. So lambda is 1 and lambda is 3. So this is eigenvalue. Okay. Any questions so far? Okay, so now we got the lambda. So lambda 1 and lambda 3. If lambda 1 in this equation, so this should be 1, right? And then we already have this matrix. So 2 times x1 plus 1 times x2 is x1. And 1 times x1 plus 2 times x2 is right here. That should be x2. So if you solve these two equations, you will get this conclusion. So x1 is equal to minus x2. Okay. So if vector is 1, 1, another vector will be minus 1, 1. Okay. So R will find you the eigenvector to satisfy this relationship. Okay, we'll see that. And then if lambda is 3, so this is 3, right? The same thing right here. This is 3. So 2x1 plus 1x2 equals 3 times x1. And 1 times x1 plus 2 times x2 is 3 times x2. So x1 equals x2. This is another eigenvector. Okay, so x1 and x2 should be 1, 1 or some other values. But R will find you the eigenvectors to satisfy this relationship. So let's look at this example. This is R. So first, we have this matrix 2, 1, 1, 2. So I created this matrix. So using the matrix function and data and 1, 2, 2, 1, we have a 2 by 2 matrix. And I enter these numbers by row. So it's the 1, 2, 2, 1, right? And then this is a matrix, and it's really simple. You can put the eigen and the matrix. It will give you the 3 and minus 1. It matches with the handy calculation, right? So eigenvalue is 3 and minus 1. And then also it returns the eigenvector. So first eigenvector and second eigenvector. Okay. And then these eigenvalues and eigenvectors, these information will be used to find the best fitting axis in PCA and EFA and the data, the reduction techniques. So we'll more talk about that in a few weeks, okay? So this is for matrix algebra. So any question about the matrix algebra? No question? Okay, so now I will move on to the maximum likelihood estimation. Okay, maximum likelihood estimation. I believe you heard a lot about the maximum likelihood estimation in your stats class, right? In stat 611, the regression will be estimated using the maximum likelihood estimation. EFA, CFA, multi-level analysis, all different types of multivariate statistics will be estimated. They are commonly estimated using the maximum likelihood estimation. So today I will briefly overview what is maximum likelihood in the high level, and then I will more talk about the details of maximum likelihood estimation. And then maximum likelihood, so likelihood is very useful to test model comparison. So the likelihood is used to test wild test or likelihood ratio test or AIC, BIC. The likelihood are all used in those tests. So we will see how they are used in those tests. So overview, the basics of a maximum likelihood estimation. This is an engine that drives the most modern statistical methods. And then additional information from maximum likelihood estimators that we'll talk about these three things: likelihood ratio test, WAR test, and information criteria. So anybody can say what is maximum likelihood estimation or Maximum likelihood? Anything.
The most probable value in a distribution.
Yeah, that's pretty close. Okay, let me give you a very simple question. Okay. We have a student and he took a math test. Okay, it's the 10 question. And he got correct, incorrect, correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. He got 9 questions out of 10 questions. Okay. And then you can guess his math ability, right? So let's say his math ability is called the data head. And then let's say this data head ranges -3 to +3. Okay. Okay, please give me the answer. Well, actually, there is no answer here, but so what do you guess his math ability located on this continuum, -3 to +3? Oh, I'm sorry, +3 this is high math ability, -3 is very low math ability. And he got 9 questions correct out of 10 questions.
2.9.
2.9. Okay, Alan said 2.9.
2.4.
2.4. Any other answer?
The average of that too.
Okay. Okay, I'll take it. 2.7. It depends, right?
On the others.
All right. So, and then I will ask you. So, who said 2.9?
I said it.
Okay. So, how did you get 2.9?
I don't know. Gut feeling.
Just got,
Put Shay in that situation. I feel Shay's ability is 2.9.
Negative 2.9.
What are you thinking about Shay in that moment?
okay. Zihao, how did you get 2.4?
I got the range here is 6, and he answered 90% right. So 6 multiply 0.9 is 5.4, and
Okay.
5.4
Okay.
plus -3, 2.4.
Okay. So that's good. And actually, you know, it's a pretty close, right? Probably he will be here, around here. But how can we get these numbers to actually, you already did the maximum likelihood estimation in your brain. So what is the maximum likelihood estimation? So, okay, so let's think about that. It's -3, -2.9, -2.7, 8, -2.7 to 3.0, okay? So based on this test result, if his latent math ability is -3, what would be the likelihood of getting this result? It's very low, right? Do you all agree?
Yeah.
Right. Yeah. Maybe here, right? What about this case? If his math ability is -2.9, what would be the probability? What would be the likelihood of getting this test result? Still very low, right? What about this case? Maybe a little bit higher, but still low, low. And then at some point, it will increase, right? And then at some point, it will hit the peak, and then goes down or like this. Do you all agree? So maximum likelihood estimation is to find the maximum. This is called likelihood. Where is maximum likelihood? Okay, here is maximum likelihood. And then find the data value here. If this data value is 2.6, okay, we can guess his math ability is 2.6. Okay. This is a very easy explanation of maximum likelihood estimation. Okay, so we'll more talk about that one. So first, you need to know what is the difference between probability and likelihood. Likelihood and probability, they are similar, but they are not same. Okay, so probability, this is the area under the probability density function, right? This is a PDF, probability density function. And then total area is, what is it? Total area is 1.0, right? So left half is 0.5, right side 0.5, maybe this part is 0.3 or 0.2, right? So these values are probability, right? So 50%, 20%, 0.5%. Okay, this is a probability. And probability is usually, to get the probability, we assume we already know the distribution. Okay, so probability is data given distribution. Actually, distribution is mu and sigma square variance, right? So this is called the parameter. Okay, so we assume we already know the parameters, so the distribution information, and then we will get the probability of this data set. Okay, so in previous example, this parameter is data. This data head. Okay, this is a parameter. But in likelihood, we don't know this value, right? This is our target task. We want to estimate this value. We don't know this one. What we have is data. Using this data, we want to estimate this one. Okay, so this is likelihood. Likelihood is the values on the x-axis. So this is a relative probability of dense PDF function. Okay, so this is probability, right? This is the probability, but this y value is called likelihood. And then likelihood is notated by L. And then likelihood is distribution given data. This is conditional distribution. So distribution is a parameter, right? And the given data. So given data, this is what we have. This is what we have. This is what we want to know. Right? Using this data, we want to estimate this parameter. Okay. So this is main difference between probability and likelihood. Okay. So, okay, so goal of maximum likelihood is to find the optimal way to fit the distribution to the data. So in other words, we want to find the parameters of this best distribution. Okay. Let's say we have this data and this is a weight. Okay. Some people are high, they're fat. Some people are very slim, low, right? And let's say we want to estimate the mean using the maximum likelihood estimation. Okay. So first, we can choose some distribution to explain this data form. Okay, it can be normal, it can be exponential, it can be gamma distribution, it can be lambda distribution, chi-square distribution, any distribution can be possible, but that distribution should explain our data very well. Okay, so in this case, we will assume it follows normal distribution because usually the weight follows normal distribution. Okay, and then okay, so and we expect the most of the weights data points to be close to the mean. If this distribution is true distribution, okay, so all the data points should be close to mean, right? So, and we expect the measurement to be relatively symmetric around the mean, right? So, but we have many different types of distribution to explain this data set, okay? This is option 1, option 2, option 3, and option 4, okay? 1, 2, 3, and 4. So out of 4 distributions, which distribution do you think explains this data most, the best?
Two.
Yeah, maybe 2, right? So here, if I choose 1, okay, if I choose 1, so this will be the mean. So I would like to estimate the mean, okay? But most of the data, most of the values we measure are far from the distribution's average. So which means this distribution does not our data very well, does not explain our data very well, right? What about this case? Okay, this distribution explains our data very well, right? So probability or likelihood of observing this weight is relatively high. So it's very high and it picked in this point. And what about this case? So most of these data is, is out of the midpoint range, mean range, right? So we can draw multiple distribution right here. What if our distribution looks like this? What would be the likelihood of getting mean? It's pretty low. What about this distribution? It's getting high. What about this? Getting high. What about this? It's pretty high. And this one. So this, let me change my color. So this distribution would explain our data point the best. It's right here. And then goes down again. Okay. So this distribution explains our data the best. So it reaches maximum likelihood. Okay. So we want location of this maximum likelihood value on the parameter right here. So this will be the mean of this estimated mean of this data set using the maximum likelihood estimation. Okay. So this is a very high level overview of the maximum likelihood estimation. And then I will show more equations related to this topic. Okay. So do you all clear about what the maximum likelihood estimation is?
How do we get the value of likelihood here?
How can we get the likelihood value? To compute the likelihood value, we need a function. In this case, we assume it follows normal distribution, right? So you will see that. You will see in the next slide.
Oh, okay.
Okay. Okay, this is a high level conceptual understanding of the maximum likelihood estimation. Okay. Right, details of a maximum likelihood estimation. So main goal of statistics is to estimate unknown estimation, unknown parameters, right? No matter what statistical analysis you use, your goal is to estimate the parameters. It could be mean, it could be slope, it could be intercept, it could be anything, right? Factor loadings, residual variance, they are all parameters. So your job is to estimate the parameters. So how can we find the parameters from the data, right? There are a couple of different approaches to find the parameters. The first one is to minimize something, okay? So what is something here? Something is error, okay? So y is our expected, predicted value, I'm sorry, the observed value and predicted value. This is error, right? So we square it, sum it, that is the sum of squares, okay? We try to minimize this error, okay? So generalized least square method, ordinary least square method, weighted least square method, WLSMV, or some other method, they all try to minimize error, okay? This is the first family. The second family is to maximize something, okay? What would be the something in this case? Can you guess?
Likelihood.
Yay, likelihood, right? Likelihood. You would like to maximize the likelihood, okay? So the typical estimation method is maximum likelihood estimation. Sometimes it is called ML, or restricted maximum likelihood estimation, REML, or robust maximum likelihood estimation, and many others. So they all try to maximize the likelihood based on your data, okay? So this is gold standard of estimator. So most software, statistical software use maximum likelihood approach. And the third one is more like, this is more like the Bayesian approach, okay? So Bayesian, so as you can see, Bayesian, Markov chain, Monte Carlo, Gibbs sampling, Metropolis Hastings, Metropolis Polis algorithm, Monte Carlo, they all use prior information. So maximum, this approach uses log likelihood, right? So likelihood, let's say likelihood, but if you multiply likelihood by prior information, that is posterior information, okay? So this approach use prior information, okay? Sometimes if you, this method works well if your model is really complicated, or if you have very strong prior information. In that case, this method works really well. But the downside of this approach is it takes really long. Okay, so MLE estimation, it runs really fast. But sometimes Bayesian method takes a day or 2 days, even 3 days. So it takes really long, okay? But what you need to know is that there are 3 general families, okay, to estimate parameters. Minimize something, maximize something, and using prior information. Okay, first, so why do we need to use maximum likelihood estimation? So maximum likelihood estimation has great properties. The first, so it as the sample size increase, the estimator converges in probability to its true value. Okay, and then second, as the sample size increased, the distribution of estimator follows the normal. This is a basic characteristics of maximum likelihood estimator. And the third is the efficiency. No other estimator will have a smaller standard error. So the maximum likelihood estimation typically produced unbiased estimator. It's very accurate, okay, based on many simulation studies from statisticians. And they found, okay, MLE is the unbiased estimator. Okay. So, right, again, maximum likelihood identifies population primary values that best fit the observed value, observed data. Okay, this is what we have, and we want to identify the population parameter. Okay, so let's talk about the univariate examples first. So maximum likelihood estimation, so that comes from statistical distribution, right? Now you understand this one, right? So likelihood value comes from statistical distribution. And then we will start from the univariate normal distribution. So this is a univariate normal distribution, right? So distribution of a univariate univariate distribution is determined by mean, variance, and data, right? So we have three things. And then let's look at this example. Let's say we have 20 employees. Okay. And then this is their IQ values. So let's say this is cognitive ability test scores, and this is their job performance. Okay. And then let's say we already know the population mean and population standard deviation. Okay, this is population mean, this is population standard deviation. I'm sorry, variance. Okay, let's assume we already know that. Okay, so using this data set, using the maximum likelihood estimation, we will try to estimate the sample mean. Okay, so this is univariate distribution. And now let's examine the distribution values for IQ values. Let's assume we know population mean and population variance. Okay, so this is population mean and population variance, right? So these values can go here. This is mean, and this is variance, right? This is 190. I will say this is 190. This is 190, right? And then we want to compute 99. What would be the likelihood given IQ score of 99? So we can put 99 here. Do you follow me? Yes? And then if you calculate it, that value will be 0.0289. Okay, again. So this is normal distribution, right? So this data set, these values are given. Let's say we assume we know these values, 100 and 190, and this is 190. Now, let's find another likelihood values given our IQ score is 87. So this 87 is data, so we put the 87 here. And if you compute this one, exponential function, this is 2.718 or something. Pi is 3.14. If you compute, that value is 0.0186. Okay. So 99 and 87, between these two values, which IQ score is more likely to be close to the population mean? $99, right? Because its likelihood value is right here. It's very close to the top, right? So in this case, it is also very useful to view the likelihood as a measure of a fit between the score and the population parameter. So in this case, high likelihood value implies the good fit to your target parameter. And a low likelihood value implies the profit. Okay, so the likelihood value, this is another measure of fit. Okay, so we always want a model with a high likelihood value. Okay, you want to compare two models, model 1 and model 2. And model 2 has much higher likelihood value. So which means that model fits much better than model 1. Okay, and that is likelihood value, and -2 times likelihood value, log likelihood, that is called deviance. This is a measure of misfit. Okay, so we want a low deviance value, right? That makes sense because it has negative sign here. We want high likelihood value. We want a low deviance value, right? Okay, so now I will move on to another example. So now let's look at the, let's say we have, this is the sample log likelihood. We can compute all the likelihood values across all different scores in this case, right? In previous example, we only compute 87 and 99, right? But using the same logic, you can compute IQ values, log likelihood values given IQ of 78. And this is a likelihood value. And you can compute another likelihood value given 84. Another likelihood value is given 84. In this way, you can compute all the likelihood values. Okay, so this is individual likelihood values of this one individual. Okay, so one individual. In this case, we assume population mean is 100. Okay, we compute all these things. And then likelihood is you have to multiply all these values. Okay, you have to multiply all these values. That is this likelihood. This notation means multiplication. Okay, so multiply all the likelihood value. That is a likelihood value. So in this example, where the highest likelihood value occurs? Maybe here, right? This is a 0.029. With the 0.008, point is increase, and here's top and the decrease again. Right? Do you all agree? Okay. So now this is we just talked about the log likelihood values, and then if you multiply all these values, that value will be really, really small, right? So 0.008 times 0.015 times 0.015 times, if you multiply, they're all 3 decimal points. So the value will be really, really, really small, right? So to avoid that computational problems, that we can put the log sign. So if you put log, so it will transform in this values, okay? But even though we transform those values to log likelihood, the characteristics that doesn't change, because this is the highest log likelihood value, but still we have, highest likelihood value, but we still can have highest log likelihood value at this point, right? So the computing the natural log of the individual likelihood value solves this problem. Okay, so this is log likelihood values. So you don't have to memorize these formulas, but if you add these numbers, all these log likelihood value, that is negative 80.828. Okay. So far, so good. Okay, so in the same way, I computed all the likelihood values given 98, given 99, given 100, given 111, 101, 102, maybe you could keep computing like this, right? And then add them up. These values are all log likelihood values. And then using these two information, this information, and this information, and this information, you can draw this log likelihood function. So this is population mean, right? This is the likelihood, log likelihood. So for example, okay, 98. When mu is 98, the log likelihood was minus 81, right? So 98, maybe, 98, 81. Okay. So what about the 102? Given the mu is 102, is minus 81. 102 is somewhere here. Okay, in that way, we can compute all the likelihood values given all different numbers. Hypothesized population mean. Okay, and then plot it. This is log likelihood function. And then we'll try to find the maximum, where maximum occurs. Okay, right here, maybe it will be 100. Then we can say, okay, estimated population mean will be, will be 100. Any questions here? Is it clear? You follow me? Okay, good. So this is log likelihood. And then in the same way, you can also compute the population variance. I don't see the example, but in the logic is the same. In the same way, we can compute all the likelihood value, the given all possible, the population value, and plot it. Okay, and then you can find some maximum value. So that is 198.6. Okay, this is maximum, and so you can find estimated the variance is 189. Okay, this is the log likelihood function for variance. And then now we'll talk about this one, the role of first derivative. So this is, this kind of process, this process is called a random search. Okay, So random search, or sometimes it is called the grid search. Okay, because we have to calculate all possible combinations, right? But it is very tedious process and computation wise, right? So your computer, I mean, definitely it will compute all possible values with the grid search process, but the most software package use calculus the derivatives to find the best maximum value. Because if we use a derivative, so derivative is, this gives us the slope, right? So if you derivative here, derivative, and then at the maximum point, derivative slope will be 0, right? So if we find the point at the slope equals 0, that point is maximum likelihood estimate, the maximum likelihood estimate, right? So in that way, we don't need to do the all grid search process. We can simply find we can simply do the derivative computation and find the best, the guessing value. Okay. So, okay, this is log likelihood, right? Log likelihood. And then this means we will do derivative to the mean, okay? And if you do that, we will get this value. And then this value should be what? 0, right? If this is 0, the sigma square, that is variance. So variance can't be 0. So that means this part should be 0. Okay, minus n mu plus sigma yi, I equals n. This should be 0. So it can go to the right. Yi equals n times mu, right? So we can divide it by n like this. So mu is this value. This is our estimator. This is exactly same as your typical mean computation, right? You just sum up divided by number of cases, right? So you will get the same result, exactly same result. And then also, this is log likelihood value, and we make a derivative to the sigma square, the variance in this case, and it will give this result, but we don't need to know this one, but this should be 0, right? So if you solve this equation, you will get this one. So this is variance. The sum of variance, sum of squares divided by n. Okay, so this is equal to the typical equation of the variance, right? So we will reach to the exactly same conclusion. But here, maximum likelihood estimation, to compute the variance of the MLE estimate, maximum likelihood estimation use population n. Okay, but sample size increase, the biasing effect is very negligible. Okay, so it should be fine. But restricted MLE, restricted MLE use n-1 instead of n. Okay, if you use restricted maximum likelihood estimation, that means you are using n-1 instead of n. Okay. Any questions?
Oh, I have a quick question.
Sure.
So you were saying using the derivatives, find the first one slopes to 0. What happens if the distribution is multimodal? Are they going to stop at the first slope at 0 and don't run the other part?
Yeah,
that's
a great question. That's a great question. So this is a very simple example, right? So if your model is really, really simple, the estimation will be done very quickly. But this is a very ideal case, but maybe let me, I can create new, okay, how can I create a new slide here? Okay, so this was a very ideal case, but in real world, and particularly if your model is very complicated, oops, I'm sorry. Complicated, your log likelihood distribution function can be like this, right? So if it starts from the left, okay, compute all the derivative and it finds, oh, here's a 0, right? It may say, okay, here is the best best parameter. But is this true? No, right? So this is called local maxima. Okay. So in many statistical software, to avoid the local maxima problem, we use multiple starting values. Okay, if you use M+ program or some other program, you can set up initial values, starting point. Okay, which means, okay, I will start from here first time, and then I reach here, and then okay, I'm going to start from here, and then maybe I reach here. Then if I start from here, I will reach here. If I start here, I will reach here. You can use many different starting values and iterate, and then find the best agreement. Okay, so I use the 100,000 starting value, and then 80% of the starting value says, here is maximum likelihood. Then we can choose this value. Okay, this is what the M+ does, and R does, and many the statistical software does. Okay. And if, okay, and then if the distribution, the log likelihood function is very complex, even you increase a starting value, you may not reach the convergence. In that case, you have to increase the iteration, number of iteration. Okay. So okay, now estimating standard errors. So the primary goal of statistical analysis is to estimate a set of unknown model parameters, right? But obtaining standard errors for the resulting point estimate is also important secondary goal. So the standard error is computed based on the slope of the log likelihood. Okay, so for example, this is log likelihood 1, this is log likelihood function 2. Okay, the both log likelihood function provide you the same answer, right? So mean is 100. It says mean is 100. But which estimation result is more accurate? So this one, right? So this flat function makes it difficult to discriminate the among competing estimate, right? Because the slope is pretty flat. But this steep, the log likelihood value, right? It more clearly differentiates the values, right? So maximum likelihood estimate from the other possible values, right? So always the steep log likelihood value, that means high slope yields more accurate estimator. Okay. So low standard error. Okay, so this is, now let's extend it to the multivariate normal case. Okay, this is, so far we talked about the univariate, right? Now we'll talk about the multivariate. So now we talked about IQ, but now we will talk about the job performance. We will add the job performance here, right? We have a 2 bivariate relationship, and this is likelihood, okay? The logic is exactly same, but the only difference is we will use mean vector, and then we will use covariance matrix. Okay, so this is mean vector, and this is covariance matrix. And then we'll try to find the best likelihood value given a set of parameters. So where is maximum likelihood values? Right here, right? And then we can go here, maybe, okay, so maybe job performance is 10 and IQ value will be 100. Okay. In that way, we can compute the multivariate normal likelihood values. Okay. So here is another example. So it's more the mathematical. So let's say this is our mean vector. Mean of IQ is 100 and job performance mean is 10.35. Okay. And then let's say this is covariance matrix, variance of IQ, variance of jobs performance, and this is covariance between job performance and IQ. Okay. We have a mean vector and covariance vector, and then we will plug these values into this. Okay, so this is, for example, this is covariance, right? This is covariance, and also this is mean vector. This is mean vector. This is mean vector. This is covariance. Okay, and then this is our data. You can try 91, plug these values, and then compute likelihood value, and 93, 2, likelihood 2, and 99.7, likelihood 3, 110, or in this way, you can compute all possible likelihood value and plot it. That plot looks like this. Okay. So this is multivariate normal data, maximum likelihood estimation. So in this case, we have 2 parameters, right? So we'll try to find the maximum likelihood value given a combination of these 2 variables. But if you have 3 variables, we can't draw it because that is a 3-dimension. That would be 4-dimension, right? But it will try to find the best maximum likelihood value given a combination of 3 parameters. Okay, if we have 4 values and a given 4 parameters. Okay, so this is multivariate maximum likelihood estimation case. Any questions so far?
So for the multivariate thing, you just sounds like a random search thing. Is there any derivative for multivariate, or is this the derivative thing?
Yeah, definitely the statistical test will do the derivative search, but multivariate, the normal distribution is generally, it doesn't follow the normal, right? So the model will be very complicated. And if, for example, if you have a 5 variable, right, it will be very ugly distribution. So it generally do a grid search method.
Okay.
Because that is not closed form. So in statistical, closed form means, for example, this is called closed form. So that means you have a single the derivative of 0 value. Okay. So that is closed form. So if your distribution is closed form, it can use the derivative, but if not, it will do the grid search. But computer will do that for you, so you don't need to worry about that. Any other questions? Okay, we have 5 more minutes. Can I use 5 more minutes? Is it fine? Okay, I will spend. Okay, so now we'll talk about the 3 different statistics. So these statistics, so all use likelihood value. Okay, so let's talk about the WAR test first. So this is a WAR test, right? So WAR test is generally WAR test is a beta and standard deviation, right? So this should be familiar in your stat 1 class, right? So this is a WAR test is estimation from the maximum likelihood minus this is hypothesized value divided by standard error of the maximum likelihood estimator. This is WAR test. This is called WAR test. But typically, our target value is 0, right? Because our null hypothesis would be, okay, slope equals 0. Slope is 0, or intercept is 0, right? So this is generally, this is a 0. Okay. And also, if as n gets large, the WAR test statistics becomes a normal distribution. Okay. So basically, this is data minus standard error data. This follows data minus data 0. I'm sorry. Standard deviation square root n data. So it follows a z distribution. Okay. And also the hypothesis test is data equals 0. So when we do the WAR test, usually WAR test use the z distribution or t distribution. Okay. So if your sample size is really big, your t distribution will be approached to the z distribution, right? But if your sample size is pretty small, in that case, you use a t distribution. So, and then this is a multivariate WAR test. Basically, it's the same. This is the same because this part, because this is inverse, variance of this estimate inverse, this is this part. Okay. So basically this is the same, but the difference is we are using metrics in this case. Okay. So in your regression class and ANOVA class, if you want to test the overall model fit, what test do you use?
F-test?
F-test, right? Omnibus F-test, right? So Omnibus F-test is used to test overall fit of your regression model or ANOVA model, but in the context of a maximum likelihood estimation, so we can still use the WAR test for the multiple parameters. Okay, so this WAR test, multivariate WAR test, testing overall significance of combination of different parameters. For example, we have 3 parameters and multivariate WAR test is significant. That means, okay, maybe one of those parameters will be significant. So here is WAR test univariate example. Okay, so in this case, I run regression analysis using ML estimator, and this is dependent variable, and this is independent variable and data. I posted this R script on the Blackboard, you can find it. Okay, and then I run it regression, and then now we get log likelihood value, right? And then this value, standard error, and t-value. So actually this p-value is based on WAR test. Right. So this maximum likelihood, this intercept data intercept divided by standard error of intercept. So 0.065 divided by 3.79 equals this value. This t-value is a WAR test value, and we are testing this value. It's not significant. But in this case, it's just significant. Okay. So do you follow me? Okay, now another common approach to test a model comparison is likelihood ratio test. Okay, so likelihood ratio test is it compares the likelihood values from full model and restricted model. Full model and restricted model. Okay, so in this situation, so if your model includes all the predicted values, predictor values, it is full model. But if your model includes no predictor or less predictor, that will be null model or restricted model. Okay, so for example, full model, in our example, job performance is some predicted by IQ score, right? So let's say B0 plus B1 times IQ. This is our full model. Our null model or restricted model is only intercept, right? So each model will produce the likelihood value and will compare that likelihood value. Okay, so -2 times log likelihood restricted minus log likelihood full value. That is likelihood ratio. Okay, so again, do we want any statistical model with high likelihood value or low likelihood value?
High likelihood.
High likelihood, right? Likelihood is a measure of a fit. So high likelihood means it produced a better fit. But deviance this is -2 times log likelihood. So this is misfit. Okay, so we want a low deviance value, high likelihood value. Okay, so I think I will stop here. I will finish this part in the next class. So I will stop here. Okay, do you have any questions for today's class? I know it's a pretty difficult concepts, but it's really important to understand the statistics. Okay, especially multivariate statistics and all different models. They use all the maximum likelihood estimation. Okay. Right. So tomorrow, like I said, I will open your quiz 1. Okay, 9 a.m. tomorrow 9 a.m. So you have 24 hours. Okay. Then what else? And then after this class, we will talk about after finishing maximum likelihood estimation, and then we'll talk about the missing data analysis. Okay, so what is the missing data mechanisms? How can we deal with the missing data? Okay, so there are many different ways: the traditional ways or modern approach. So we'll learn both. Okay, all right. Okay, so I will see you in next class. Thank you.
Thank you.
Thank you.
Thanks, Bill.
Thank you.
Do you want to